pleasure to welcome Sabyasachi-san. As Pierre pointed out, Sabya is an extremely well-known glass scientist, and we are very excited to have him here. He's a professor at UC Davis and got his PhD in 1996, I assume, from Stanford, and interestingly in geosciences, right, Sabya, if I'm not
Yes.
mistaken.
Yeah.
So don't want to take up too much time. The floor is yours. So thanks a lot, Sabya, once again.
Okay. Thank you, Krishna and Ankit, Pierre, for that nice comment on Austin to begin with. We all will miss him greatly. So without further ado, let me share the screen and start the lecture. Um, Let me know if you have any difficulty in seeing my screen. But
No,
is that good?
yeah, it's great. So,
Perfect.
Sabya, the floor
Okay.
is yours.
All right. So, um, this is something that's not directly on glasses, but nevertheless, considering the occasion, I would like to dedicate the talk to Austin's memory. I have very fond memory of chatting with him at conferences, and I always considered him to be one of the role models in my field. And I will be talking mostly about liquids. Some of them will turn into glasses, although that's not the subject of the talk today. I'll mainly stay in the liquid state. And I will be talking about one of Austin's favorite liquid, which is one of the most important liquid that we know, that's water. And so to some extent, that will be pertinent for dedicating this talk. I wish he could be here. So without further ado, I'll be talking about behavior of liquids when they're put in very, very tiny spaces that are nanometer sized space. So the point is why nanometer is important, and we will see what happens. But we all know already for the last couple of decades, at least, there has been a lot of research on how properties of materials suddenly show emergence of new behavior when they are very, very tiny in size. So size matters. We know about quantum confinement and change of band gap in semiconductors that are called quantum dots. We know about plasmon resonance in metal nanoparticles and superparamagnetism in tiny magnetic particles where the magnetization direction flip-flops randomly. But also there are, besides these quantum effects, there are also classical thermodynamic effects, which primarily come from the fact that the surface to volume ratio increases a lot when you go to tiny size. It's mostly surface. If you consider a tiny particle, almost 90% of the atoms could be near the surface. So in that sense, surface energy term dominates and can change actually phase equilibria, change properties of materials. Here are a couple of examples. One is one of Professor Alex Navratsky's work, who I believe is currently at ASU, when her group from UC Davis did this work. This is the phase equilibria of TiO2 nanoparticles in rutile, brucite, anatase, these polymorphs. They change their relative stabilities as a function of size. And on your right is this plot of magnesium aluminate spinels that came out of my group in collaboration with Professor Ricardo Castro, who made these samples. He showed that the hardness of the spinel nanoparticles increase quite a bit as you lower the size. So this is plotted as a function of inverse square root of size. So as size decreases, the hardness increases in this fashion. And then we showed that also concomitantly, what changes is the magnesium aluminum order disorder in spinel sites, which is called inversion. So the tetrahedral, octahedral order disorder changes following the same trend, and so does the surface to volume ratio. So these are quite interesting properties of materials, solids in the solid state, that come from size. But today I'll talk about confinement of liquids in very tiny spaces, as I said. The question is, why should we care about these kind of situations? Well, I'll give you three examples, which I hope will convey the message of their importance. So on your left, these are nano-sized channels in cells of organisms, plants and animals, which these nanochannels are called aquaporins, which allow fast um, in and out motion of water into the cell. Otherwise, you will have to depend on diffusion through the cell wall, which is a very slow process. So these nanochannels are a hot topic of discussion because the behavior of water, as we know in the bulk, changes, as I'll show, a lot when you put them in these kind of tiny spaces. In a similar fashion, you can use tiny spaces for biological immunoassays. For example, you want to do single molecule DNA separation and study. In these cases, this is the nanofluidics, where you have these tiny nanometer sized channels that allow only one kind of DNA, depending on their shape and size, to go through for single molecule analysis. This was fabricated by a laser on a piece of silicon. And then finally, this is a DOE basic research area, which is the controlling the subsurface fracture in rocks. And that is very, very important parameter for very efficient oil and gas extraction from nanopores of rocks that are sedimentary rocks like shales, which have nanometer size, tens of nanometer size pores where the fluid behavior changes. But also the reverse process of carbon dioxide sequestration, where you put water carbon dioxide mixture and inject into these tiny spaces inside rocks underneath the Earth's surface. And as it is being studied, it's being found that the water CO2 phase equilibria changes quite a bit when you get to these tiny spaces. So this is an important topic for all these from all these points of views. Now let me see why I'm a little bit stuck here. Okay, here I go. So what I will be talking about is the phase behavior of fluids under nano confinement. And I'll be talking about both thermodynamic and kinetic issues with that. So let's see what it is. What are the things that I'll be stressing on? So this is a volume temperature diagram that is well known among, at least, very well known among glass scientists because we look at it almost every day, which is that when you take a liquid and cool it, its volume decreases, density increases, and it has two options. One is that it can suddenly undergo a first order transition to a crystal, which is shown by this vertical dashed line. And that transformation can happen over a narrow range of temperature because first order transitions are driven by nucleation and growth often. And so the crystal nuclei, for example, need to grow in the liquid. So over a certain temperature range, crystal and liquid can coexist. But eventually, below the melting point, the liquid turns all into crystal in that kind of a phase transformation that we all know in the bulk state. What I'll show you is that that may not be necessarily true, and crystals and liquids can stay together practically forever or for a very, very long time when you keep them confined in nanospaces. All right, so the other option for the liquid to do is to change its volume continuously and go below the melting point. Because of kinetic reasons, it can bypass the thermodynamic transition. Atoms cannot move fast enough to arrange in an ordered lattice. And then this is called the supercooled liquid state, which is metastable below the melting point. And at some point, its viscosity increases so much that it basically becomes like a rigid solid, and we say it has undergone glass transition. And so this is a purely kinetic transition, which is denoted by this T sub G or Tg, as I'll be calling it, and this Tg, or the glass transition temperature, as well as the Tm, the melting point, I will show in different liquids. They are affected strongly, these kinetic and thermodynamic processes, once the liquid is confined into tighter and tighter spaces. So the point is, what could be happening in terms of the structure of the liquid, right? Because that will be controlling whether it will be going into a crystalline state or a glassy state, how the melting point will change or Tg will change, etc. And there one needs to consider two effects. One is just the size effect, which is also the so-called Gibbs-Thomson type effect, where we know that, for example, for first order transitions, we need to worry about change of vapor pressure with curvature, and the tighter the space, the higher the curvature, and therefore, the lower could be the melting point. That's why nanoparticles melt at a lower temperature than their bulk counterparts. So that's a size effect, but the structure is fairly homogeneous throughout the confined space. On the other hand, you can have also interfacial effects between the confining medium surface and the liquid surface. So at this interface, the structure of the liquid could be different compared to that in the interior, and the structure could gradually change, or there could be a core shell type structure with a two liquid type scenario. So these are some of the possibilities, and these are controlled by the interfacial effects. So in this talk, I'll be discussing two things. One is the freezing melting transition, like I showed you under nano confinement, and I'll be talking about the water freezing into ice. And in the second part, I'll talk about glass transition in nano confinement in various pore spaces, three-dimensional confinement in various very well characterized pore spaces. And so a few words about the matrices that we use for these confinement studies that I'll be talking about for the rest of this talk. So these are all some sort of silica matrices. They were very, very carefully prepared. These are some TEM pictures showing the regularity of these nanochannels in these materials, SBA16, FDU5. These are various types of mesoporous lattice architecture of nanopores running down and arranged in a specific lattice structure. And these were synthesized very identically, or as much identically as possible, using the same type of silica source, same type of block copolymer as structure directing species, etc. So they are extremely well characterized. And it is very important to have similar things so that you are comparing apples to apples, because in the literature, especially in the beginning, there are a lot of studies where people are randomly looking for nanoporous materials, and they just compared apples to oranges. So here, the credit of synthesizing these very, very carefully goes to my colleagues, Professor Mike Bartle at University of Utah in chemistry, and also to Professor Subhash Risbad in my department. So these are a couple of examples of such materials that we have used. Here are some X-ray diffraction from these mesoporous lattice. They agree very well with the literature values. So these are not novel materials, but they're very well characterized materials that have been reported in the literature in the past. And so I'll be talking about, for example, SBA15, which has this hexagonal lattice of cylindrical nanochannels of about 4 or 5 nanometer in diameter. Then these are SBA16, which have these spherical pores and attached through cylindrical openings, shown in red. FDU5, which has two sort of a bicontinuous lattice of cylindrical pores. So there are cylindrical pores, and then at the junction, there are spherical junction between these cylindrical pores. So two sides, one is spherical, pore size, another is the cylindrical pore size. Here also there is a spherical pore size and a cylindrical pore size, but these are all interconnected. So the liquid, if it wants, can go and visit the next, the other channel, adjacent channel. And then I'll also talk about Vicor as a confining medium, except these are not commercial Vicors. Vicors are phase-separated glasses where you leach out one of the phases to create these continuous but tortuous pores, nanopores. But in our case, these are further treated. The commercial Vicors have 5 to 8 nanometer pores, but these have 11 to 15 nanometer pores because we treated them further with acid and so on. So that's the material, that's the confining medium that we'll be using. And now to the material behavior or liquid behavior in these pores. So first is the freezing melting transition. And so here are a set of, typically you study freezing melting behavior. First thing you do is to run a differential scanning calorimetry scan. So these are scans of heating scans of water, as you can see very clearly from a very quick look that when the pore size is 15 nanometer, the melting point is, the onset is somewhere here, whereas the onset moves to a lower temperature when you go to 4 or 5 nanometer. So clearly size has a very strong effect. Nanometer size creates a depression in melting point, and this is nothing not known before. This is a very well-studied phenomenon of depression of melting point in nanospaces following the Gibbs-Thompson law. That's what you would predict. These are some examples of the materials and the corresponding scans. What is new, though, is this is the first time we saw that if you have two pores, albeit interconnected, you can see two different melting points of water. And mind you, I forgot to mention that we are not looking at H2O, we are looking at D2O. The reason being we also want to do spectroscopy on them, and deuterium is one of the nice nucleus to do nuclear magnetic resonance or NMR spectroscopy, which is something that I like to try on different materials. So that's why we chose D2O. There's nothing different from H2O in it, except the melting point is around 4 Kelvin instead of, 4 degrees centigrade instead of 0 degrees for water, for H2O. So this behavior of two different melting points was quite interesting because this indicates tremendous amount of heterogeneity in dynamical heterogeneity in the water confined in these nanospaces. That tells me that, when I go to SBS 16, these 3.2 nanometer cylindrical pores, water in it, is not talking to the water in the 5.5 nanometer spherical pore. If they would be freely exchanging and diffusing, then there should be just one melting point, but instead we can distinguish two melting points as if water in the cylindrical pore does not talk very efficiently with the water in the larger 5.5 nanometer spherical pore. They can diffuse eventually, but over the time scale of the DSC measurement, you can clearly pick out this strong heterogeneity in the dynamics that will homogenize otherwise the melting freezing behavior. So now here is a plot of all these melting point depressions, delta sub Tm, meaning how far it was depressed. So 0 would be the bulk value. How far it was depressed from the bulk value as a function of inverse size of the pore space. And here you can see you can get a nice relationship using a slightly modified Gibbs-Thompson relation, which is this, where in the denominator is just not purely R, but minus a thickness, which is a typical modification of the Gibbs-Thompson relation, which takes into account a thickness which is sort of a monolayer of water that would be stuck and not doing anything, because it is strongly um, adsorbed on the surface of the pore, or this is the pore liquid interface monolayer that does not do much. And we found that this T is about 0.39 nanometer, in excellent agreement with simulations by, say, Burg and Stiefel. For one, there are many others who did this kind of simulation of water in nanopores, and they saw that there is a statistical monolayer of water molecules with about this thickness, that's shown in blue, that does not do any activity and never freezes. So with that, you can see a nice relationship that follows the Gibbs-Thomson relation. Here, K is a constant that actually includes, for example, the enthalpy of melting and molar volume of ice and those kind of parameters. So this is nice, but also what Burg and Stiefel saw is that, is this brown layer, which is about a nanometer thick, where the water is highly structured, they found in their simulations. And they called it shell water as opposed to the core water at the center of the pore, which is more like bulk water. And they said that the shell water is highly structured because of its strong interaction with the interface, and so it must be a slow dynamic. It must have a slow dynamic compared to the dynamics of the core water. So in order to see those things, one now needs to do spectroscopy in order to see, are there structural signatures of those kind of water in there. So these are our Deuterium Nmr Spectra in one of the confined media. They all look pretty much the same in terms of their behavior with temperature. So here is the lowest temperature spectrum we collected at 193 Kelvin all the way to 283 Kelvin, which is significantly above the melting point of D2O. Now, NMR for the uninitiated is a spectroscopy where we look at the transitions between spin energy levels in a nucleus, which is affected by the local bonding environment of the nucleus or the atom. So it's an element-specific technique. But also NMR is a technique that you can use to study dynamics, and I will show you a couple of examples of that in this talk. So first of all, what you see here is a very broad signal and a narrow signal on top of it. And you can decompose the signal into these two types. So this peak at the center we know corresponds to liquid-like water, and this peak gets narrower and narrower, and eventually this entire broad component decreases and everything gets very, very narrow. So this is the behavior if you put a drop of water inside a magnet and you can collect an NMR spectrum that will look like this. This tells you that the line shape is so narrow. It's a typical liquid-like NMR line shape, which says that all the water molecules are moving extremely fast. They're rotating, tumbling, diffusing, whatnot. And that's what makes the NMR signal very narrow. But as you cool it down, you can see this emergence of this very broad signal. And I'm not going to go into the details of why the shape of the signal is like this. So you have to take my word for it that this is extremely well understood and can be theoretically calculated. And this is the calculated line shape in teal. And this corresponds very well to the line shapes observed for single crystal ice as well as polycrystalline ice. That's not to say that this is coming from crystalline ice. This could be amorphous ice. We don't know. And this could be a mixture of amorphous or crystalline ice. We don't know about those things. But all we know is that there is a solid-like component and a liquid-like component. Eventually, with increasing temperature, the liquid-like component increases in its fraction as it should, but well below the melting point, the nominal melting point, which is, let's say, around here, well below that, you can see the presence of this liquid-like component. And this stays forever. It's not like, this is as a function of rapid cooling. At each of these temperature, we can hold it for, say, up to an hour. We tried and nothing happens to the line shape. So So this liquid-solid coexistence or water-ice coexistence seems to be very, very stable and with specific ratio as a function of temperature. This indicates that there is a static heterogeneity inside the nanopore and presumably a layered structure, because as you cool, different layers of water freeze and the rest of it stays liquid, and then it progresses some more freezes, and this solid-like signal increases in fraction with respect to the liquid-like signal. This becomes more apparent if we plot the liquid-like population, basically the area of this narrow peak divided by the total area of the signal. And here you can see that, and this data point is from literature done in MCM41, which is the smallest of the pore. But here you can see that, as you lower the size, the appearance of the appearance of the drop of the liquid-like population moves to lower and lower temperature, as it should because of the freezing point depression. But also, one thing to note is that the drop is the steepest, from purely liquid fraction to almost purely solid fraction. The drop is steepest for the smallest size pore and for the largest size pore. In between, they sort of go gently down from fully liquid-like to fully solid-like spectrum. So this is not difficult to understand if one realizes that the smallest size pore, it's probably very difficult to have multiple layers with different types of water structure inside the pore. It's probably all very homogeneous because it's just 2 nanometer size, and all the water is behaving identically and they freeze within a very narrow range. On the other hand, for the very large pore size, most of it is like the core structure, and very little of the stuff is in the shell around the thing, because it's pretty large pore of, say, 15 nanometer or so. So the shell-like water that I showed before, this brown layer, shell-like water fraction is pretty small. Mostly it is, a core-like structure, and therefore they also, freeze over a narrow range. But in between, you can have a progression. So the water near the shell behaves differently than near the core, or near the interface behaves differently compared to near the center. So this is like a layer by layer freezing of water inside these pores. And you can see this also very clearly if I take the slopes and plot them as a function of pore diameter, that it goes through a minimum here. The slopes are quite steep for the lowest and for the smallest and the largest pores. The same thing you can do, or not the same thing, but you can also derive from these transformation versus temperature to a distribution of activation energies for these freezing process, or the water mobility associated with the melting freezing dynamics, and we get activation energies ranging between about 30 to 40 kilojoules per mole, which is in very good agreement with other studies on water using, say, dielectric or neutron scattering techniques. So that's all good. Now, we think that this provides a direct explanation of this long-standing puzzle in the water behavior in nanopore in the literature. So this is just one of the many papers that have been published over the years that shows that if you plot the time scale of water dynamics, in many cases these are measured by dielectric relaxation, let's say, or neutron. This is in 18 angstrom pore, 14 angstrom pore, but both show pretty similar behavior, that the relaxation time or the dynamical time scale is strongly non-Arrhenius, meaning the activation energy is strongly temperature dependent at slightly high temperature, but as you lower the temperature, this is as a function of reciprocal temperature, so temperature goes down to the right. As you lower the temperature below a certain point, it ceases to become non-Arrhenius and behaves in a pretty Arrhenius fashion. So activation energy becomes independent of temperature. And people assign this behavior to a fundamental transition of water from fragile. This is called a fragile behavior, again going back to Austin Angel's influence in the literature. He's the one who coined these terms. Fragile denotes non-Arrhenius behavior. Strong is the Arrhenius behavior. It has nothing to do with the mechanical strength or fragility. But this fragile to strong transition was believed to be happening in a homogeneous body of water inside a nanopore. But now we have a natural explanation of this, where we are saying that this layer by layer freezing gives a natural explanation. So here, the water freezes and the remainder of the water, which is mobile, you are getting the signal from that. So this is the water, not the ice signal. The water signal, as water gets more and more strongly confined, at beyond some point, since this is a layer by layer process, beyond some point, it is really confined not in the entire pore, but surrounded by the ice around it. And so it is very, very strongly confined, and therefore its entropy decreases because the available configurations decrease, because the confinement size becomes comparable to the cooperative rearrangement size, and then it becomes Arrhenius. So the layer by layer freezing provides a natural explanation of this fragile to strong transition. And this heterogeneous dynamics is something we have seen also once we plot the line width, logarithm of the line width as a function of reciprocal temperature. This line width is the width of this liquid-like line here in the Deuterium Nmr spectrum. So this is the line width is related to how fast or slow the water molecules are moving. And you can see that below a certain temperature, in each case, the line width shows a fairly nonlinear, sort of a sudden jump below a certain temperature, indicating that as water gets more and more confined upon freezing, it becomes more and more rigid in its dynamics and slow. And this kind of slow dynamics comes in because of its self-confinement as the layers of ice around it grows. So in conclusion for this part of the study, I would say that we have seen strongly spatially heterogeneous glassy dynamics of confined D2O. Even in its melting point, we have seen two melting points in interconnected pore, which was something totally unexpected to us. And this extreme spatial heterogeneity actually translates into a layer by layer freezing process, because every layer, as a function of its distance from the center or from the periphery of the pore, has a different kind of structure probably. And these structures freeze at slightly different temperatures. So it's a continuous layer by layer process, which eventually gives rise to this fragile to strong transition. All right, so on to the second part. Now we are going to switch gear to from a simple liquid, or not so simple liquid, but simple transition of liquid to crystal, to a more complex kinetically driven process of supercooling of a liquid and glass transition. So for that, I want to start with, again, a simple liquid, which is glycerol. And this is unusual in a material science seminar to talk about. Probably water is okay because of its great importance, but glycerol may not be okay. But this is, trust me, this is important, as I have noted or tried to emphasize the importance of glycerol, as it is probably one of the most widely used glass forming liquid in terms of its use in medical vitrification of blood cells, food, wine, pharmaceutical, personal care, all the way to manufacturing of explosives. So glycerol is important. It has a melting point of 291 Kelvin, and the TG, or glass transition temperature, of 185 Kelvin. It's a hydrogen bonded or weakly hydrogen bonded molecular liquid where the density of hydrogen bonding is believed to be temperature dependent. But we're not going to get into that details. I just want to denote that there are 3 carbon sites, because we will be doing carbon NMR on this to understand the dynamics of these molecules in the liquid as we cool. And we'll be particularly focusing on 1 carbon. So we did a site selective enrichment. Not we, but we bought the chemical, which is enriched in this CHOH site. These are CH2OH. This is the only CHOH site. So we'll be looking only at this carbon. And we'll be looking at the dynamical averaging of NMR interactions because of the anisotropy of the NMR effects on this carbon atom as they get averaged as the molecule tumbles and rotates in liquid state. So first of all, a word on confinement, again going back to one of early works by Alex Navratsky's group, that this is glass transition of nano-confined glycerol, where you can see the glass transition temperature changes. It actually increases with decreasing pore size. So this is inverse of the pore size. And this is a continuous behavior. So so what is typical of glycerol then is an increase in TG with increasing confinement. Okay, please keep that in mind when we go to this next slide. So here are a bunch of experimental carbon NMR spectra of that carbon site in glycerol. I'm just showing you the confined glycerol. We also collected data on bulk glycerol, obviously, as a starting point. And then what you can do is you can simulate these line shapes at different temperatures. And again, you have to take my word for it that this is theoretically very well understood how to do these simulations, very standard in NMR literature at least. And by simulating, you can get the dynamical rotational time scale of the glycerol molecules, how fast they're rotating. And this rotation also, you can figure out that this rotation is isotropic. So it's not about any specific axis in the molecule, but it's rotating around all possible axis orientation. So the axis gets randomized with time. So this isotropic reorientation is what it is called. So when you plot this isotropic reorientation time scale, log of that, as a function of inverse temperature, then we get these triangles for the bulk glycerol. And what I'm showing you with this solid line is the shear relaxation time derived from the viscosity of glycerol, supercooled glycerol. And you can see that over 5 orders of magnitude in time scale, the viscosity or viscous flow of glycerol is controlled by this isotropic reorientation of the constituent molecules. Okay. In contrast, this is the data we got for the confined liquid, okay, which shows that not only this is very, very slow at any temperature until you get to a much lower temperature where there seems to be a crossing, but within error that could be disputed. We could not go any lower in temperature, but at least in this temperature range, it seems like it is not only Arrhenius or strong behavior with a single activation energy that is temperature independent, unlike bulk, but also it's very, very slow moving in nanospace. With sometimes, at high temperature, the difference could be 3 orders of magnitude in the time scale. So now, problem is that glass transition of this guy is 196 Kelvin, which is confined in these 2.2 nanometer pores in MCM41. On the other hand, the bulk TG is 185 Kelvin. So this TG of the confined glycerol we know is higher. But then TG is defined as the temperature where the tau is about 100 seconds, right? So it'll be 2 on this scale. And you can see if I extrapolate these two curves to a value of +2, then the TG the temperature corresponding to the confined one would be extremely low compared to the bulk. So this is the reverse of what we are actually observing. So NMR says the TG has to be very low if we take the tumbling process or isotropic rotation process of the molecule. But then the DSC, differential scanning calorimetry, says otherwise. So the only way to explain the discrepancy is to say that the glycerol under confinement is a different liquid compared to under bulk, so that the actual alpha relaxation or the primary relaxation is something that must be along this line, which has nothing to do with the single molecule rotation anymore. So this becomes then a beta process, which is diverging from the primary relaxation alpha process in glycerol. So that means there must be a change in the equation of state of glycerol if it's a fundamentally different liquid. And again, NMR chemical shift can come in handy there, because for glycerol we have found out that the NMR chemical shift depends on the volume or the density of the liquid. And here is a plot of pressure dependence. We did high pressure NMR on glycerol, and this is the pressure dependence of the isotropic chemical shift, and this is the temperature dependence in the inset. So you see they go in different direction, and their slopes are consistent with the corresponding thermal expansion coefficient versus bulk modulus of glycerol, which shows that chemical shift is indeed controlled by the density of the glycerol. So in that case, the bulk glycerol chemical shift is somewhere here, obviously at 0 MPa. But the confined glycerol shift turns out to be here, which says that this glycerol has a density, the nano-confined glycerol has a density corresponding to a pressure of about 290 megapascals. So this may sound bizarre, but then we went back to the literature and found out that glycerol's viscosity, or TG, is actually known as a function of pressure. This is an old paper by Herbst that came out in Nature in the early 1980s, where they did a diamond anvil cell type study of viscosity. Very challenging measurement, but that says that at 290 megapascal, indeed, a TG should be about 10 Kelvin higher than the TG of the bulk. And that's exactly what DSC finds. So our finding that the glycerol density is quite different in the nanopore is consistent with all this, and says that there is indeed a change in the equation of state. So it may not be surprising that there is the alpha relaxation process is fundamentally different, and what we are looking at, the same process that controls alpha relaxation becomes a beta relaxation in the nano confined state. And now I want to finish the talk, if I can get 5 more minutes, on glass transition of another molecular liquid, this time much simpler than glycerol in the sense that this is a van der Waals bonded liquid, no hydrogen bonding. This is the orthoterphenyl, OTP as it is lovingly known in the glass community, at least. So we put OTP in all these nanopores in mesoporous silica, and we saw that the TG actually drops with size, and the TG drop follows Gibbs-Thomson type relationship, linear relationship, delta TG like delta TM. Gibbs-Thomson relationship obviously does not predict anything about TG, but similar relationship can be found, has been reported in the literature for both TG and melting point. But one of the interesting things is, unlike water in all those pores which followed a single line, OTP follows 2 different linear trends, one in Vicor, tortuous pores, large pores, whereas straight, small pores in well-arranged lattices, mesoporous lattices. So this means that the interfacial interaction must be quite important for orthoterphenyl, not just the size effect or the pure confinement effect. But more interestingly, we were more interested in finding out the dynamical heterogeneity side of glass transition in these nano-confined spaces, whether there is a similar thing like we saw for melting of D2O. So here are data on OTP confined in these single pore sizes, and you can see the TG depression compared to the bulk TG, which is TG sub B, corresponding to the bulk TG. And you can see that there is one TG, but as soon as you put orthoterphenyl into these two pore bicontinuous structure, again, mind you, these pores are continuous and interconnected. So OTP molecules have every opportunity to travel from one pore to the adjacent pore, which has a different diameter. Yet we see signatures of two glass transitions in these cases, as well as the bulk signal. The bulk signal comes from some of the OTP outside the sample, on the surface of the sample. And that's obviously the strongest because there's a lot of that compared to those in the nanopore. But the point is then, with water, we saw that a structural difference results into the melting point difference, the structural difference in layer by layer freezing. And the structure of water is different from, between water near the periphery compared to that near the core. Similarly, the water structure must have been different in the two pores, and they were not communicating with each other or homogenizing over a time scale. For glass or for supercooled liquids, it's easy to calculate that time scale because, or the diffusion length associated with that time scale, because we know we are close to TG. So the relaxation time is on the order of about 100 seconds. Diffusion coefficient for molecules in OTP has been studied. Self-diffusion coefficient turns out to be around 10 to the minus 16 centimeters square per second. So from this back of the envelope calculation, the diffusion length turns out to be about a nanometer. So, on the order of nanometer scale diffusion length over the relaxation time, this could have homogenized and given us 1 TG, but it does not, which says that, there is coexistence of structural and dynamical heterogeneities that are preserved over these nanometer size length scales, or the length scales of pore dimensions. So the slow population and the fast population are remaining that way for time scales much longer than the average relaxation time. So, these kind of dynamical heterogeneities are also well known in the bulk. But what was the big question for glass forming liquids is that, are they associated with structural heterogeneities as well? Are they spatially coincident, structural and dynamical heterogeneities? And I think this study points strongly towards that there must be a spatial overlap between these regions of structure and dynamics that are different. So in conclusion, there is a tremendous slowdown in the transport properties and apparent fragile to strong transition in the equation of state, and also related change in the equation of state of glycerol that we have seen. And interestingly enough, this fragile to strong transition is also apparent and may not be real, because what we are comparing is the same dynamics, but it was in the bulk, it was controlling the shear relaxation or primary relaxation or alpha relaxation, but in the nano-confined liquid, it's probably converting to a beta process, and probably a more cooperative, much slower alpha processes there that we don't know about. And then finally, we also have shown, I hope, there is extreme spatial heterogeneity that is manifested in two distinct melting point and two distinct TG for water and OTP. And then finally, a couple more slides, one on future directions, what remains to be done, which is basically a whole lot. One needs to, this is the burning question, is it possible to separate and isolate the spatial versus interfacial interactions in nano confinement, pure size effect, and also interface effect, how to separate that, how to design an experiment, which is the so-called self-confinement experiment. And then systematic investigation of equation of state, I think could be very interesting in future. This is just, we just scratched the surface with glycerol. Is the shape important? Shape of the confining medium. Sort of like going back to the quantum effect of plasma on resonance, where the shape of the nanoparticle is important. Right? Can you do superheating instead of supercooling? So you take a solid under nano confinement, and how far you can heat it above the melting point, and whether there is also a layer by layer melting that you can observe. And final slide on acknowledgement. So this study was supported by this was part of an EFRC, Energy Frontier Research Center grant between multiple institutions by US Department of Energy, Basic Energy Science. And my collaborators are my graduate student, I-Ching Shah, who did all these experiments except those on the glycerol, which was done mostly by myself. And then Professor Risbad and Professor Bartle from my department and from University of Utah on kindly synthesizing these amazing samples with very well characterized pore spaces for this study. So with that, I'm happy to take questions.
I think we really need to, it's past our cutoff time. So thanks a lot, Sabya. We had really good attendance today, 83 people logged in with unique ID. So we typically average around 70. So that's above average performance.
That's better than average, yeah.
But this was awesome. Thanks a lot, Sabya.
Okay.
And, Ankit is going to be extremely mad, but we still haven't shipped. We ordered polos, for people to wear it before the seminar, and we express ordered it, and we haven't last semester, and we haven't shipped it to anyone. So at some point you'll get one.
Krishna, I'm already getting emails from the first of the seminar speakers. Where are our polos?
Okay,
Yeah.
so next time you ask me to give a talk, I'm not going to do that without the phone.
Yeah, okay. Will do. Thanks, Sabya. Thanks a lot, and have a great day.
See you, Pierre.
Bye.
Thank you, Krishna. Thank you, Sabya. Bye.
Bye, Ankit.
Bye.
Bye.